This is the screencast for section 6.5, example 3, finding three partial fractions. It can't be true. Yeah, it is. Three partial fractions. And just to give you a heads up, they tell you this example will be our most laborious problem. Find the general solution to dy dx equals that polynomial divided by a polynomial where the degree in the denominator is higher, so we're all set to use partial fractions or to do partial fractions. That denominator, though, needs to get factored a little further. X squared minus 4 can factor into x minus 2 times x plus 2. So if I'm going to take the antiderivative of both sides, because we're finding the general solution to a derivative, so I am going to take the antiderivative. Now this means that I can really just take the antiderivative of a constant over the first binomial plus a constant over the second binomial plus a constant over the third binomial, and those binomials are from the factored denominator. Well, if I found a common denominator, I would basically be setting myself up for this situation where A would get multiplied by the other two, B would get multiplied by the other two, and C would get multiplied by the other two, which means then that that expression, A times x plus 2 times x minus 1 plus B times x minus 2 x minus 1 plus C times then x minus 2 x plus 2 will equal the original numerator, 6x squared minus 8x minus 4. I just need to pick values of x to help solve for A, B, and C. So first I'm going to say if x equals 2, then B and C both get multiplied by 0, and so that will help me solve for A equals 1. If x equals negative 2, then A and C both get multiplied by 0, which helps me solve for B equals 3. And then if x equals 1, A and B get multiplied by 0, and C is 2. So which gives me the antiderivative, 1 over x plus 2 dx, plus another antiderivative, 3 over x plus 2 dx, plus another antiderivative, 2 over x minus 1 dx. I can separate an integral over addition because an integral means add, and that's your addition property of integration. So now let's take those antiderivatives. Antiderivative of 1 over x minus 2 is the natural log of absolute value x minus 2. Antiderivative then of 3 over x plus 2, well, I can leave 3 as a coefficient and then take the natural log of absolute value of x plus 3. And I'll do something similar for the third piece here, 2 times the natural log of absolute value x minus 1. Now if you want to use your log properties, if you add a bunch of logs of the same base, it's really the same as multiplying by what you're taking the log of. Now of course 3 will have to become an exponent of the absolute value of x plus 3, and 2 will have to become an exponent of x minus 1. So then really in this answer you wouldn't even need absolute value for the last part here, because it's being squared, it would always be positive. And then of course do not forget your plus c's, your constant at the end. We can combine all the plus c's from each of these antiderivatives into one plus c at the end. The now try problem, number 17, simply says solve the differential equation. So you need to notice that integration by parts and use substitution, I'm not saying they wouldn't work here, but they probably wouldn't work here. Really it looks like since the degree in the denominator is higher, that integration with partial fractions might be your best bet. So the first thing I'm going to do is factor out that denominator. So I'm going to pull out an x and then break that difference of squares into x plus 1 times x minus 1, which means I'm really trying to find the antiderivative of a constant over x plus a constant over x plus 1 plus a constant over x minus 1 dx. So now to set up my partial fractions, A, the constant A can get multiplied by x plus 1, x minus 1, B by the other two, and then C by the other two. And that would equal my first numerator of 2. So now I'll pick and choose my x values to help me solve for each of the constants. So if x equals 0, I get to solve for A, which would be negative 2. If x equals negative 1, the 0 of the middle denominator, then B equals 1. If I get x equals positive 1, then I get to solve for C, which equals positive 1. So I'm taking the antiderivative of this, with each of the constants in place in the numerator, which I can separate each of those integrals so that I can use natural log. And then that would be negative 2 as the coefficient, natural log of the absolute value of x, then plus the natural log of the absolute value of x plus 1, and then the natural log of the absolute value of x minus 1. Now if I want, I can make that negative 2 an exponent. Now, I have addition between all of these logs, so technically they're all going to get multiplied together, but that negative 2 exponent is going to drop the x squared down to the denominator, and then x plus 1 times x minus 1 is x squared minus 1, still an absolute value. So this would be my final solution to this differential equation using partial fractions.